Hello everyone, welcome back to AlgoScribe. In today's video, we will be solving the problem of finding the container with most water. This is a very important problem. This will help you understand the two-pointer approach. It is a very simple and intuitive one. As we go and understand this problem, you will be able to understand it as well. So we'll go through the problem statement first. The problem description goes like this. So basically, we are given an array. This array is basically going to hold heights. Let us assume them to be as a height of walls, right? So imagine we are having an input like this. Okay. Also, please do imagine the sides are closed. Now, the basic intuition is that, so the basic idea is that we have to find two pairs of walls such that the amount of water these two can combinedly hold is going to be the maximum, right? We are going to solve this using the two pointer approach. We are going to ideally point in two places of the array, and we are going to compute in a optimal way. Okay, so how do we solve this? Assume that we are pointing to the ends of the array, right? So how do we calculate how much water these two pairs of walls can hold? So it should be calculated based on the min height of min of either walls. So assume that this is 1 and this is we'll say this as 2. Okay, minimum of 1 and 2 into the distance between them. What should be the distance? 1, 2, 3, 4, 5. The distance is 5, right? So min of 1 and 2 into 5 is going to give us 5. Let's say it is 5 liters of water. Okay. Where it is? Yeah. Okay. Okay. Now that we understand how to calculate how much water two pairs of walls can hold, we are going to try and maximize the water. So these two pairs can only hold 5 liters, but the potential, the potential of each wall varies, right? So the potential or the contribution of this particular wall is going to be only height 1, but the potential of, I mean, the capacity of this wall is 2. So this will probably give a better result than holding on to this one. So what we are going to do is we are going to move our pointer and point it to this one. Now what we have two walls of height 2. The minimum of these two is going to be 2, and the distance between them is 4. Yes, so basically we have moved 1 unit away. Now 2 fours are is 8, right? Now again saying that this is in liters, so it can these two pairs can hold 8 liters. Okay, now, these two walls are of similar capacity. So in this case, what we do, we choose anything. I'm going to go and choose to move the left side. Okay. Now, moving the left side one step further, we are back to a smaller wall at height 1. So what we are trying to do is we'll again calculate up and until these two say that this is the left pointer and this is the right pointer, up until left is less than or equal to right. Until this condition turns false, we will iterate. All right. So that is what we are going to do. I hope that this is made clear. So what we are trying to do is we are going to move each pointer that we believe that is going to not hold much value. We will keep a pointer in a wall that is taller. That is the basic understanding, right? So let's start to code it out. Okay. Let us say we have max water. Max water so far is 0. We have initialized it to 0, and we have the left pointer at index 0 and the right pointer at height dot length -1. All right. So as shown here, we started with the ends of the walls. So we are starting with the ends of the walls, and the condition that I told was while left is less than equal to right. All right. I think we don't need to go up until equals, because if we go to the equal, what it means is these two pointers are going to point to the same wall, which means the distance is zero, and anything multiplied by zero is zero. So it will never contribute. So we don't have to do the equal to, right? Now what we are going to do is the left wall int left wall is equal to height of left. Right, int right wall is equal to right. And now we are going to calculate the current area. The current area, what did I say? Math dot min into left wall, right wall into the distance between them. This is the distance, right? The two pointers are basically pointing the index. If we subtract the right minus the left, we will get the distance between them. So we will update our max here. Now comes the actual functionality. What we are going to do is, if left wall is less than right wall, what we are saying is left wall's potential to give a better solution is not there. Basically, right wall is taller than the left wall, so we are moving the left wall in the hopes that we find a better wall. All right, that makes sense. Yeah, so we are going to move the left wall, else we will move the right wall. Okay, now we will return the max what over here also. Okay, what is the problem here? Sorry, this should be minus minus. So basically what when we are going to move the right from right to left, and left moves from left to right. Right, yeah, this is good. But one more optimization that we can do is, uh, think that we have a wall. Okay, okay, so we have a left wall and we have a right wall. Okay, now this left is smaller than the right, so obviously what we are going to do is we are going to move it to move the left pointer. So assume that the next wall is smaller than this. So basically we have determined that this wall itself is of less importance than something that comes after it, meaning something of a lesser distance. I mean, the distance also contributes to the answer, right? This distance is greater, but what we are assuming is we are going to meet a bigger left wall. But in fact, what we saw next was a smaller one. So we can loop through the input up and until we meet we meet a bigger wall than the current left wall, at least. So at least that will probably yield to our result. So that is what we are going to do. What we are going to do is left wall while left is less than right. So basically by making this optimization, we should not by any chance fall off the input, right? So that is also something important that we have to maintain. Left is less than right, and height of left is less than left wall. So so we have moved one pointer. So currently the pointer points at this. Assume the pointer points at this, and what we are looping to find is a better left wall. And how do we do that? We are ensuring that the input doesn't. The pointers do not fall off the input, and also the height of the current left. The height of current left is this. The height of current left is less than the height of the current left wall. Until this condition meets, we are going to move the left pointer. Likewise, here, we are making sure that the left doesn't fall off. The pointers do not fall off the right. Also, height of right is less than right wall. Here we should make right minus minus. All right, I think we are good to go. Yep. Okay, so I'll give a rough walkthrough again. So here, if you see that we have initialized the final result and the two pointers. These are the two pointers pointing to the input array. We are making sure that the left pointer is always lesser than the right. Why? Because if they are equal, it is no point. And if they are going further away, I mean, crossing each other, that means basically we have parsed all the input up until then. Now we initialize the height of the left wall and the height of the right wall. Here we calculate the area in which water can be there, the current area between the two walls. Right now we recalculate the max water. Okay, now what we do, if left wall is lesser than left wall's height is lesser than the right wall, we hope that we find a better left wall. So what we do, we move the left pointer one step forward, and also we move the left pointer as many steps as required until we find a left wall that is greater than at least the current left wall. Likewise, here what we are going to do, we are going to move the right pointer to the left side. Likewise, here as well, we are going to find a right wall that is better than the current right wall. After doing all this, we would have computed the area in which the maximum water can be held.